Good morning students. Welcome to the chemistry class. Now our today's topic, that is integrated zero order reaction. Okay, so now first question that comes in our mind, that is what is zero order reaction. So students, let's see the definition for zero order reaction. It is the reaction whose rate is independent of the reactant and remains constant throughout the course of reaction. It means it is independent concentration of the reactants, and then I could write the equation is rate is equal to K concentration of A raised to 0. So when A raised to 0 means A raised to 0 is nothing but 1. So I could write the equation is rate is equal to K. So but this is our final equation. So we see the rate of reaction is dependent in this case on rate constant only. And in this not dependent on the concentration of reactants. So I hope you got to know that what is zero order reaction. So students, we will see here how to derive the equation for rate constant for zero order reaction. So we consider a reaction that is A is a reactant and A is giving product. Okay, so as the time is increases, at a time of increases, that the concentration of reactant goes on decreases. So this is nothing but the rate of reaction. So for this I could write the rate of a reaction as rate is equal to minus D concentration of A upon dt. Here minus means concentration of reactant is decreases, and now since we are talking about zero order reaction, so we could write zero order reaction is the power of 0. So let us see, according to rate law, rate is nothing but K into concentration of A. But since the zero order reaction, so that is this experimental values of X component in this case will be 0. X's value is in this case 0. So let us see what is as zero order reaction. Rate is equal to K A power of 0. So let us see what else we can do with these things. So now equation can be written as rate is equal to K, right? Rate is equal to K. Okay, but we have also got the rate K also. We can mark this equation as 1 and equation 2. So that for equating both the equation 1 and 2 will get, so equating equation 1 and 2, we will get minus dA upon dt is equal to K. So I can do the further process like minus dA is equal to K dot dt, and should the negative sign to one side, that is dA is equal to minus K dot dt. But this equation is a differentiation equation for a zero order reaction, right? So let us see what happens when we are going to integrate it. Okay, so integrating the equation, we could get this thing, right? Integrated dA is equal to minus K integrated dt. But integration should be unlimited, that is low limit and high limit. So I would consider when a limit t is equal to 0, right? If we consider time t is equal to 0, the concentration of the reactant A is 0. Okay, so would have been A naught. Okay, then time is increases and time t is equal to t, right? T is equal to t. Then the concentration of reactant would have been 80. So since we know that integration of dx is equal to, dx is nothing but x. So similarly the integration should be similarly the integration of dA, right, dA will be A, but with A limits, that is upper limit, when A is 80 is A0 is lower limit, right? So when time t is equal to t, and when low limit t is equal to 0, so we get this equation, right? So up to this equation, what we can get, this instead of A, we'll write the upper limit of AT minus and lower limit A naught, that is concentration of AT minus concentration of A naught, right? That is, so we will get final V as AT minus A naught is equal to minus KT. So what we are going to do is, now we are going to relate with the rate constant and the further part, that is the further like that A naught minus AT, A naught. And so by arranging the above equation, that we have got KT is equal to A naught minus AT. Simple. And this equation can be final is written as K is equal to A naught minus AT upon T. So this is the final equation that we have got, or we have made a relation between rate constant for a zero order reaction. I hope you have understood and you have got to know that how to derive the equation for the rate constant for zero order reaction. So students, see you in our next class. Bye bye.